So imagine you just got your graded stats test back. You look down and boom, you scored an 85 on your third exam. You're feeling pretty good about it, right? But almost immediately, your mind jumps to the massive final exam coming up next week. Now, let's say you have a whole data set of scores from previous students who took both of these exact tests.
Here's the big question. Since you scored an 85 on exam 3, can I mathematically predict your final exam score using all that past data? Like, can we literally just draw a line through a scatterplot of old scores and accurately guess your future grade? Well, the mathematical answer might actually surprise you, because we can't just draw a line and hope for the best. We absolutely have to test our data first.
By the end of this explainer, you are going to completely understand the concept of testing the significance of the correlation coefficient. We'll cover the exact rules behind it and show you exactly how to apply it to real-life examples, like predicting that final exam score. All right, let's just dive right in.
To really wrap our heads around this, let's use a real-life analogy. Picture this. You're making a massive pot of soup. You want to know if it needs more salt, but you obviously aren't going to drink the entire pot just to find out, right? Instead, you taste a single spoonful. In statistics, that spoonful is our sample correlation coefficient, which we call R. We calculate R from our small sample of data. The entire pot of soup? That represents the true overall relationship for everyone in the world. We call that the population correlation coefficient, represented by the Greek letter rho. So we're basically using our spoonful, R, to estimate the entire pot, rho.
And that brings us to our main goal today. Testing the significance of the correlation coefficient really just means we're deciding if the linear relationship we see in our small sample data is actually strong enough to model the relationship in the entire population. We're trying to prove that the trend we see in our spoonful isn't just some random coincidence, but a true reflection of the whole pot.
Now, you might be thinking, wait a minute, if I calculate my sample R and it's a really high number like 0.9, why can't I just immediately start predicting exam scores? It is such a common student confusion. But here's the deal. The reliability of your linear model doesn't just depend on a high R value. It heavily depends on N, the number of observed data points in your sample. Think about it. A high correlation in a sample of just 2 people is completely meaningless. We always have to look at both the R value and the sample size together to figure out if it's significant.
To do this properly, we set up a formal mathematical test. Let's translate these math symbols into plain English. Our null hypothesis, h sub 0, is that rho equals 0. This basically assumes the true population correlation is exactly 0. Then, our alternate hypothesis, h sub a, is that rho does not equal 0. The crucial thing here is understanding what these actually mean for us in the real world. If we stick with the null hypothesis, it means the correlation is not significantly different from 0. Basically, there's no real linear relationship, and we absolutely cannot use our regression line to predict exam scores. But if we find enough evidence for the alternate hypothesis, it means the correlation is significantly different from 0. That tells us there is a real linear relationship, and yes, we can use our line to predict outcomes.
So, how do we actually choose between the two? Well, there are 2 equivalent methods. Let's look at method 1, the p-value method. First, you use a calculator function, like linreg t-test, or computer software to find your p-value based on your data. Second, you compare that p-value to a designated significance level. In most standard cases, and for this entire explainer, we're going to use a significance level of 5%, which we write out as alpha equals 0.05.
The decision rule here is honestly beautifully simple. If your calculated p-value is less than your 0.05 alpha level, you reject the null hypothesis. You declare that R is significant. But if your p-value is not less than 0.05, you do not reject the null hypothesis. Your R is not significant, and you just walk away without predicting a single thing.
Let's make this super concrete by jumping right back to our third exam versus final exam problem. Let's say we have past data from 11 students. We plug those 11 data points into our calculator, and it spits out a p-value of 0.026.
Now, I want you to think about this for a second. We have a p-value of 0.026. Our alpha threshold is 0.05. Since 0.026 is clearly less than 0.05, what's our decision? Do we reject or not reject the null hypothesis? Well, because our p-value is lower than our significance level, we reject the null hypothesis.
Okay, so that was method 1, and now let's move to method 2, the critical value method. This method doesn't use a p-value at all, but it's going to give us the exact same logical result. Step 1, find your degrees of freedom. This is just your sample size, n minus 2. Step 2, look up that number on a 95% critical values table to find your target boundaries.
In step 3, compare your actual sample R to those table boundaries. Picture a number line acting kind of like a trap. Your table gives you a negative critical value and a positive critical value. If your sample R falls somewhere inside that trap, between the two numbers, it's just too close to 0 to be significant. But if your R is strong enough to fall outside the range, either way negative or way positive, it is significant.
Let's look at another concrete example. Suppose you compute an R value of negative 0.567 from 19 data points. Our degrees of freedom would be 19 minus 2, which is 17. Looking at our table for 17 degrees of freedom, our critical values are positive and negative 0.456. Since negative 0.567 is further out on the number line than negative 0.456, it completely misses the trap. Therefore, yes, this correlation is definitely significant.
Let's try one more. Say you compute an R value of 0.134 from 14 data points. The degrees of freedom is 14 minus 2, which gives us 12. The table tells us our critical values are plus or minus 0.532. Now look at our R of 0.134. It's stuck right between negative 0.532 and positive 0.532. It is just too close to 0. So our decision here is no. This is not significant, and you absolutely cannot use this data for prediction.
Time for a quick retention check. What if you calculate your sample correlation R and it comes out to exactly 0? But you have a massive sample size of 100 data points. What do you think happens? Is it suddenly significant just because of the large sample?
The answer is that a correlation of exactly 0 is literally never significant. No matter how massive your degrees of freedom are, an R of 0 will always be trapped right smack in the middle between the negative and positive critical values. A 0 correlation just means there is absolutely no linear relationship to model whatsoever.
Let's bring this critical value method right back to our original exam problem. Remember, we had 11 students, so our degrees of freedom is 11 minus 2, which is 9. If we look at the table for 9 degrees of freedom, our critical boundary is 0.602. That is the hurdle our data needs to clear.
For those 11 students, our actual calculated R value was 0.6631. Let's compare them. Because 0.6631 is greater than 0.602, it falls outside the trap. It is significant. Notice how both method 1 with the p-value and method 2 with the critical value just gave us the exact same conclusion. The correlation is significantly different from 0.
And here is the final, highly satisfying resolution to our original question. Because we tested R and found it to be mathematically significant, there is sufficient evidence of a linear relationship. So yes, we can mathematically predict your final exam score from your 85 on the third exam using the line of best fit. The math totally checks out.
Before we wrap up, let's quickly summarize the key rules we've learned today. 1. Always evaluate your correlation R alongside your sample size N. 2. If your test leads you to reject the null hypothesis, your relationship is significant and you can predict. 3. If you do not reject the null, you cannot predict. And 4. Even if it is significant, only ever make predictions within the domain of the X values you actually observed in your data.
But wait, stop right there. This next part is incredibly important. There is a hidden assumption behind everything we just did today. Testing the significance of the correlation coefficient only works if your data points actually fall along an approximate straight line pattern in the first place. The Y values must be normally distributed around that linear trend. If your scatter plot looks like a giant U shape, this specific linear test just isn't going to help you at all. Which actually leads us to a pretty fascinating question. What happens when reality is messy? What if your data doesn't form a straight line? Or what if you have one massive outlier that completely throws off your R value? How do we handle data that absolutely refuses to behave? Well, that is exactly what we are going to explore in our next explainer. Thanks for joining me today, and keep